determines AD, you need not check it. B determines F, you need not check it. D determines C, you need not check it. You assume that it can be proved. The following functional dependencies can be projected into the following decomposition. However, BC determines E has to be explored. BC determines F has to be explored, and A determines EF has to be explored, right? So only 3 of these functional dependencies you need to prove whether the functional dependencies exist in the relation or not, right? So what you do is that you store the left hand side of the functional dependency in a variable Z. So you are expected to find Z intersection R1, Z intersection R1 closure, Z intersection R1 closure intersection R1, Z intersection R1 closure intersection R1 union Z, right? And then you are going to update the value of Z, right? Again, you are going to repeat the same process. Z intersection R2, Z intersection R2 closure, Z intersection R2 closure intersection R2, Z intersection R2 closure intersection R2 union Z, and so on. So here in the value of Z you have B, C, D, F. So it which means that B, C determines F can be proved, right? Similarly, we continue with the third relation, and you can prove BC determines C is also proved, right? Then you have another relation, another functional dependence which has to be proved. A determines EF. So for A determines EF, again you are going to store the value of A in Z. Again, you are going to continue with Z intersection Ri closure intersection Ri union Z, and in third iteration you get that Z intersection Ri closure intersection Ri union Z, A determines F is also proved, right? So you can follow this, right?
Yes, sir.
Yes.
Right.
Yes, sir.
So now I think it's time for us to solve some problems and explore whether the functional dependency holds good. So let me share some other document. Right. So I have questions 4 and 5. So it's a simple relation, capital R with attributes A, B, C, D, and the following functional dependencies holds good. Like A determines B and B determines C, right? And you have the relation R decomposed into 2 fragments, R1 and R2, with attributes A, B, and AC respectively, R1, R2, R3, right? R1, R2, and R3 with the attributes A, B, AC, and AD respectively. Check whether it's a lossy or lossless decomposition, and it's a dependency preserving decomposition or not, right? So you can make a note of it, and you can solve the problem, question 4, and update me, right? So you're expected to solve the problem, and you can share the solution randomly. One of you can share the solution. Right. So you are familiar with the problem of checking whether a decomposition is a lossy or lossless decomposition. So Samuel, what are the conditions for checking whether a decomposition is a lossy or lossless decomposition? Samuel, Lokesh Arnagiri. Lokesh. Lokesh, can you hear me? Supriya Prasad.
Yes, sir. Hello.
Yeah, yes, you are audible.
Yes. So the conditions for lossless decomposition, right, sir?
Yes.
Okay. So if R is decomposed into R1 and R2, or up to Rn, then the union of all of them should be R. That is the first condition. Then, second condition is that intersection should be not null, and third condition is that R1 the closure of the closure of R1 intersection R2 should logically determine either R1 or R2, or it should no, it should logically determine either the super key of R1 or R2. So these
Correct,
are the conditions.
correct, right, correct, Supriya. So can you solve the problem 4 and share the solution?
Yes, sir. Just a second, sir. Um, um, so can I take 5 minutes to solve, or should I
No, you can
say?
take your own time. Like everyone, you can everyone can solve it independently. You can take a piece of paper and
Okay.
pen and solve it. Take your own time. So initially, you can give the solution for checking whether the decomposition is a lossy or lossless decomposition. Then you have to explore whether the dependency is preserved, functional dependency is preserved in the decomposition or not.
Yeah. Yes, sir. Okay.
So are you familiar with checking for functional dependency? Have you noted it? How to calculate it? Are you familiar?
Yeah, the previous class. Yes, sir.
Okay.
Should I say that? Um.
Not necessary. You can
Okay.
solve the first subdivision and show us,
Yes,
and
sir.
you can move on to the second subdivision. Right. So you can everyone can solve the problem independently, and you can message me if you have got the answer, correct solution, so that I can call you for support.
Sir, can you show the example problem, sir? Hello.
Example problem, right? Use
Yeah.
it. I can
So for
even
reference.
yeah, that's it. I can even upload it in your. Let me upload it in the materials, right? 2 minutes, 1 minute.
Okay, sir. Thanks.
Right. So I have uploaded the problem with solution dependency preserving decomposition, because I think everyone is familiar with checking whether the decomposition is a lossy or a lossless decomposition. The thing that you need to explore is that you need to check whether whether the problem is a dependency preservation decomposition, or dependency is not preserved in the decomposition. So the solution is there. Solution for the last class is available in the course materials. You can explore it and get me the solution for question 4. So you can message me if you have done it. Question 4, if you have completed question 4, you can message me.
Sir, it's not dependency preserving.
It's not dependency preserving, right?
Because D
So
won't
it's
be present in the
lossy
file.
as well.
It's lossy as well,
Yes, sir.
Yes, sir.
right? So Viswanathan, can you share your?
Yes, sir. Can I say it?
Yeah, I think you can say it again. You can upload it and you can show it if it is visible. I think it will be.
Okay, so 1 second.
I will stop my sharing.
Yes, sir. Can you give me 1 second?
Right. You can share the solution with everyone and you can explain it.
So can you see my screen?
It's partially visible. Partially
Yes, sir.
visible.
Yes, sir.
Notebook is partially visible. Yeah, now
Now,
it's fully.
yes, sir. So it's very rough. So I'll explain. So I've taken Z is equal to A first because the first relationship is A gives C. So I've taken that where I did Z intersection R1, which is R1 is AB. So I got A. A closure is ABC. So ABC intersection R1 is AB. Then to update Z, Z is equal to AB union Z, which is AB. So A gives B is proven. So we update Z is equal to AB now. So, but Z doesn't contain C yet. So we take Z is equal to AB, and then we take R2 as AC. So AB intersection AC is A, and A closure gives ABC again. ABC intersection R2 will give AC. Again, updating Z will get AC union Z is equal to ABC. So A gives C also proven. But the Z doesn't contain D yet. So we take Z is equal to ABC as the new updated Z. R3 is equal to D. So Z intersection R3 is R3 is AD. Sorry. So Z intersection R3 is A, and then A closure is ABC again. ABC intersection R3 will be A again, and A union R3 will give ABC. So D won't be present in the end. So it's not preserving, dependency preserving.
Okay, thank you, Vishwanathan. I think
Shall I stop sharing?
Yeah, you can stop sharing. I think you didn't solve the first subdivision, right? Have you checked whether it's
Lossy,
lost?
no, sir. I didn't solve lossy yet. I'll solve it.
Yeah, I will. Supriya, have you done it? First subdivision at least. You would have done it, right?
So the lossy decomposition, yes, sir, that I did. It is lossless.
Can you share it?
Yeah, yes, sir. 1 second, I will share it. Sir, can you see the screen?
It's visible.
Yes, sir. Okay. So first we are going to check the union, and union is ABCD, which is R, and then we will take intersection of R1 and R2, which will give us A, and A closure will be ABC, which is super key of R1, and then we will take ABC intersection R3. So that will give us ABC intersection AD, which will equal A, and then A closure is again ABC, which is a super key of again R1 intersection R2, that is R12. So it is lossless.
Is it correct?
Oh wait. So could you show us the question again? Because I don't think the closure way would give you ABC.
No, it's
Yeah.
lossless only, correct.
Oh yeah.
So
Yeah. So it's correct. It's correct. So yeah, it's correct. It's lossless. Yeah.
It's lossless, huh?
Yeah. So
Yes,
it's
sir,
lossless.
it's lossless.
So it's lossless, but it's not preserving the dependency, right?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So let us now move on to the question 5. So let me share it. Right. So question 5, you have a similar problem. You have your relation with attributes A, B, C, D, and there exists functional dependency like A determines B and B determines C. Now, same thing we are going to decompose into 3 relations. So both the problems look similar. Only thing here we are going to decompose it into 3 relations: R1 with attributes AB, R2 with attributes BC, and R3 with attributes AD. Again, you need to check whether it's a lossy or lossless decomposition, and whether it's a dependency preserving decomposition or not. So Udit Kumar, I think you can make it, right?
Yes, sir.
sir, I've come done, sir. Can I share?
Subramaniam has
Yes.
done.
Yes, sir.
Okay, Subramaniam, you can share us the first part, and Udit
Oh,
can
whether it's
run it,
lossy or loss.
lossy or lossless. Right.
Sure,
Okay. You
sir.
can or you can share. You have done it. You have done completely, right?
Yes, sir.
Okay. You can share it. Use it. I will get you some other problem to work out.
Okay, sir.
Subramaniam, you can share us once you complete, or if you have done it, you can share it.
Yes, sir. Is my screen visible?
Yeah, it's visible, Subramaniam.
Yes, sir. So we have two dependencies, which is A gives B and then B gives C. So corresponding to relation R1, which is AB, we can prove that A gives B is preserved. And then to with respect to the relation R2, which is BC, B gives C is again preserved. So these are the only two relations. So we need not use those formula and then check if that other dependencies which are not given as relations are preserved. So in total, the given dependencies are preserved. And then going for lossy or lossless decomposition, we again take the union of all three relations and check if it's equal to the original relation, which is R. So the condition satisfies. And then we take the intersection of subsequent relations. So we start with R1 intersection R2, and AB intersection BC we get as B, and then taking the closure of it, B closure would be BC, and clearly it's a super key of R2. So the condition is satisfied for in the first step, and then merging those relations to give R12 as ABC, and then taking R3 into account, and then taking the intersection of R12 and R3. We take ABC intersection AD, which is A, and then the closure of A would be ABC because A gives B and then B gives C. So ABC is again a super key of R1. So we can merge them, and then R123 would be ABCD, which is equal to the original relation. So all three conditions is satisfied, and the decomposition is lossless.
Right. So I think here the dependency preserving top component is simple. I think I didn't check it. Yeah, it's
Yes,
very
sir.
simple.
Both the relations give the
Yeah,
dependency, so you need not use the formula.
right. So I wanted to give you some problems in dependency preserving only, but I think it's quite simple. Anyway, so I think it's quite simple. Anyway, we'll explore one more problem to check whether the dependency is preserved in a decomposition or not.
Yes, sir. Can I stop sharing, sir?
Yeah, you can stop sharing, Subramaniam.
Oh, yes, sir. Thank you, sir.
Thank you. Right. Right. So the outcome of today's class is like I want you to become familiar with checking whether the dependency is preserved in a, you need to know whether how to check whether dependency is preserved in a decomposition or not. I think the second problem was quite simple. It doesn't check for any dependency preservation. So let me get you some other problem. So let me share whatever we have discussed in the previous class, right? So Subramaniam has done this problem, right? He has solved whether the decomposition is going to be lossy or lossless decomposition. He has proved that it's a lossy decomposition, right? This let us leave it lossy. Right. Right. So this problem, so you can look into this third problem. So already it has been proved that its decomposition is a lossless decomposition. So let us leave it. Only thing you need to check whether the dependency is preserved in the decomposition or not. So again, A, B determines C is proved, C determines D is proved, D determines E, F, right? So here you need to prove whether the functional dependency D determines E, F is valid, and F determines A is valid, and D determines B is valid, right? So you can note it down. So this is this third problem. So we are expected to check whether the functional dependency is preserved in the decomposition or not, right? So here I think we'll be proving only three functional dependencies. You need to validate whether D determines EF is true, and F determines A is going to be true, and D determines B is going to be true. So I'm not sure about the solution. I think it may be complex to prove it. Anyway, you can start working on it. So initially, let the value of Z be D. So Z intersection R1. So Z intersection R1 is going to be null, right?
Yes, sir, null.
Yes,
So
sir.
it cannot proceed, right? Z intersection R1 closure union
It'll
is
be null.
yeah. So check it out. So I don't have any solution for this problem, but I think it can be proved, right? It can be proved whether it's a dependency preserving decomposition or not. So I want you to work out and come up with a solution. right? So you need to check for different values of or Z intersection R1, Z intersection R2 closure, intersection R2 union Z, and so on. So you need to check for different combinations. So you need to check
So
for.
we're taking D1 for now, right? The first question, right?
So you need to take D.
Yeah.
D
D gives EF.
D determines EF. You need to prove initially D determines EF, followed by F determines A, and followed by D determines B. So you need to check for all the three relations. Z intersection Ri, Z intersection Ri closure, intersection Ri union Z for three relations.
So I think it doesn't preserve because for
It
F
gives null
determines
for.
A. F determines A, we get EF, so it doesn't determine A.
Right. So all the three dependencies they are not preserving. Like F determines A is also not possible, I think.
Yes, sir.
D determines B is also not possible, right?
Yes, sir.
Yes, sir.
Right. So this decomposition is a lossless joint decomposition. However, the dependency is not preserved in the decomposition, right? Yeah, A, B, C, B, F, D, I, J, D. Right. So can you check with this question 1? Here you need to prove only one functional dependency. A determines DE. Whether A determines DE is so you need to check whether only A determines DE is true or not.
Yes, sir. I think it's not preserved again.
Can you share the answer?
I haven't written it down, sir. I just have it in mind. Can I say or should I write it down in short, sir?
Or you can say it. You can say it, Subramanian.
Yes, sir. So taking the intersection of A with any other relation other than R1 would give a null because of the absence of A in the other relations. So we take A intersection R1, which is A, B, C, D. So A is the answer, and then taking closure of it. So we take Z as A, and then closure of A is A, D, E, I, J. So if you take the intersection of A, D, E, I, J with R1, it will be again A. So you take A union, which is Z, which is A. So A union A would be A, and you don't have any D, E in that. And if you uh, repeat the process again, you'll be stuck in a loop where you'll have only A as Z, and then you won't have any D or E component inside it.
Right. Then you should try with Z intersection R2, right? AC.
Sir, but you won't have any
AC
intersection.
between AC intersection D is going to be null, right?
Yes.
Okay. And again, union is, yeah, that's it. Right. Right. So hope you are familiar with work
So you're not audible, sir.
So I got disconnected. Only I'm back. Am I audible now?
Yes, sir.
Yes.
Yeah, that's it. So we'll start a new topic in the next class. I think you are familiar with dependency, checking for dependency, preserving decomposition in today's class. So we'll start with some new topic. We'll study the different normal forms. So next class onwards, we'll study first normal form, second normal form, 3NF, third normal form. We have BCNF, boys code normal form, 4NF and 5NF. So we'll study the definitions for different normal forms. We'll explore solutions for different normal forms. So we have like a canonical cover. One more problem will be about working with canonical cover that we'll study in our later classes. We'll also study how to find out super key and candidate key in a relation. So unit 5 is about normalization, working with different normal forms, 1NF to 5NF, checking whether a decomposition is a dependency preserving decomposition or not, and checking whether a decomposition is a lossy decomposition or not. Canonical cover will study whether some minimal functional dependency is enough. Some FD is redundant, we can remove it using canonical cover. And right, so we'll study about, we have already studied about the different types of anomalies. So we'll I think maybe in a week or something we'll try to complete this unit 3. Right, so thank you for your participation. We'll meet in the next class with some new topic.
Thank you, sir.
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 Thank you, sir.